Now we will discuss the agents or causes of metamorphism. The main cause of metamorphism are increases in temperature and pressure as rocks get buried underneath the surface by other rocks or subducted at plate boundaries. Another agent of metamorphism is interaction of rocks with hydrothermal fluids. This happens on a much smaller scale than these increases in temperature and pressure. So interaction with hydrothermal fluids typically creates something called contact metamorphism at the contact between different rock bodies, whereas the increases in temperature and pressure are a result of burial or subduction of very large quantities and volumes of rocks. Thirdly, another agent of metamorphism is application of stress. This also happens at the large scale. In geology, we like to call this large scale the regional scale. So one example of this is before at point A, temperature is 20 degrees Celsius with a pressure of 1 bar at Earth's surface. As those rocks get subducted in a subduction zone, they get buried underneath other rocks and are at 15 kilometers depth beneath the Earth's surface and become metamorphosed. These would be at 450 Celsius and 6 kbars at the same point respectively. So these rocks have undergone increased temperature and pressure, likely interaction with hydrothermal fluids at the local scale, and then application of stress. Temperature and pressure both increase with depth. Importantly, pressure is equal in all directions beneath Earth's surface, whereas temperature increases only in the z direction, or the direction from the surface towards the center, or the radial direction. Heating of material adds energy to the rock, which can break and reform chemical bonds in minerals. This is referred to as recrystallization. Importantly, in recrystallization and in metamorphism in general, the whole rock does not melt. The added heat just causes changes to take place for individual minerals within the rocks. Pressure causes materials to collapse, forming different bonds and causing phase changes or metamorphic reactions. So on the right we have a picture of a typical geothermal gradient, where at 0 kilometers depth we are at 0 kbar and 20 degrees Celsius. As we increase in depth to 20 and 40 kilometers, we get similar increases in pressure and temperature. Hydrothermal fluids are very hot water solutions that have minerals dissolved in them. These speed up metamorphic reactions by increasing the rate of diffusion, allowing more elements and chemicals for the rock that has been subjected to these fluids to interact with. So they carry the dissolved material from one location to another. Metasomatism is a term that refers to compositional changes that take place during metamorphism. Application of stress is the third metamorphic agent, and it's defined as the application of force over a unit area. So compression involves squeezing of a material, and tension involves stretching of a material. These two are opposites. Shear is an angular force that moves material sideways relative to another part. So if you imagine compression in two equally opposite directions, but if you move one of those directions slightly over so that the compression is oblique to one another, then you get shear. When we think of stress, we need to think in terms of 3 dimensions. So differential stress occurs when the stress is not equal in all directions. In metamorphic rocks, grains will align perpendicular to the direction of compression. So if we've got India crashing into Asia to create the Himalayas, we have the creation of a differential stress likely, and in the direction of convergence we get squeezing, just like the book and the floor with the dough ball in between. We see this in mineral and rock assemblages in metamorphic rocks in areas that have undergone convergence. Now we'll discuss the types of metamorphic rocks. There are two main types of metamorphic rocks, which are foliated and non-foliated. Foliated metamorphic rocks contain a preferred orientation of minerals that have undergone differential stress. Examples include slate, phyllite, schist, and gneiss. Non-foliated rock does not contain a foliation, indicating that stress was applied equally in all directions, or the protolith did not have any minerals that have preferential alignment, meaning that the protolith did not have any clay minerals. All of the foliated rocks mentioned above have some sort of clay mineral in them to illustrate the foliation. So some non-foliated rocks include quartzite, hornfels, and sometimes marble, although marble can also have foliations. Slate is the finest grained foliated metamorphic rock, and it's formed by the metamorphism of shale or mudstone. Slaty cleavage forms in response to compression. So here we have a diagram explaining how slate forms after compression in two opposite directions. Slate is a common roofing material, and the reason for that, its flatness, is because of its foliation. Phyllite is also a fine-grained metamorphic rock, and it's the result of preferred orientation of white mica minerals. This clay has recrystallized to form the tiny mica flakes in phyllite. Schist is also a foliated rock, but it is medium to coarse grained and includes a schistosity, which is a preferred orientation of large crystals of mica. So notice that the difference between these different foliated rocks is related to grain size, not necessarily composition. Gneiss is a metamorphic rock containing alternating layers of dark-colored or mafic and light-colored or felsic minerals. This has a slightly different composition than the schists, phyllites, and slates, and its protolith likely had a heterogeneous composition as well. Schists, phyllites, and slates, mostly protoliths, were claystone and mudstone, but gneiss may be a little bit more heterogeneous. Now we move on to the non-foliated rocks. Quartzite is a metamorphosed rock consisting almost entirely or entirely of quartz. On the left we have a sandstone protolith or parent rock. After recrystallization during metamorphism, it is turned into a quartzite, where all of the grains are not cemented together by a cement and held together with a matrix. They are recrystallized where their boundaries have been sometimes fused together and definitely intergrown with one another. Marble is a metamorphosed limestone. So on the left we have a limestone showing some structure. After metamorphism, a lot of sedimentary structures, typically all sedimentary structures, get destroyed in the increased heat and pressure. Some marble is foliated, however, if the limestone did have adequate clay minerals present. Next we discuss metamorphic grades, and these are a result of different temperature and pressure ranges at different depths. So metamorphism takes place under a range of conditions, and metamorphic grade is a classification that relates to these conditions under which the rock formed. So you'll see at low temperatures and pressures we have no metamorphism This is where sedimentary rocks are created at these temperature and pressure ranges. But as we increase in temperature and pressure, we actually are changing mineralogy, and we are changing the structure of the rock so as to start getting low grade and increasing intermediate to high grade metamorphism. On the diagram, we have some lines that show when wet granite starts to melt and when wet basalt starts to melt. So once you go up into the high grade metamorphism, you are actually starting to melt the rock itself. And once you've fully melted the rock, you are no longer a metamorphic rock. It has become a melt that will cool and solidify to become an igneous rock once again. Blue schist metamorphism is a unique type of metamorphism, or a unique grade at low temperatures and high pressures. And the low temperatures are a result of water being subducted at a convergent boundary, which cools the rocks that are being subjected to increased heat and pressure as they go deeper within the earth. So we've got high pressure in blue schist facies metamorphism and low temperatures as a result of the water. This produces special rock assemblages. I'd like you to take 5 minutes and draw and label this diagram for part 2 of your lecture activity. Also write down 3 to 5 sentences explaining the diagram. So metamorphic grades, as you might have guessed, correspond to different metamorphic rock types. As temperature and pressure increases and grade increases, we get increasing changes in the rock type. So as we go from shale, a shale protolith, low grade, it's called a slate. Mid grade, it's phyllite and schist. And then high grade, it's a gneiss. And we see the mineralogical changes as we go from clay to sillimanite.